Hello, everyone. I'm going to give you an introduction to USCi's silicon carbide technologies with a specific focus on understanding our cascode switches. My name is Anup Bhalla, and I'm the VP of Engineering for USCi. USCi has three different types of released products. There are junction barrier Schottky diodes that you can get from us. They're best in class. Uh, Commercial products are at 650 and 1200 volts. We also make custom devices at 10,000 volts and high temperature devices, which are customer specific. We specialize in normally on JFET technology, specifically trench JFET technology, because this allows us to make the lowest on resistance switches in a wide range of voltage classes. These devices tend to be very reliable and robust, especially for things like short circuit and unclamped inductive switching. And by themselves, the devices are capable of very high temperature operation. In order to turn them into useful normally off switches for basic switching applications, we do cascodes, where the device is combined with a highly optimized MOSFET, uh, all in one package, so that the final device is a drop-in replacement for an IGBT plus FRD or a MOSFET with a built-in Schottky. It can be driven by a standard gate drive, gives you excellent diode behavior, short circuit, and avalanche robustness. So why we have these technologies is best understood from this slide. The normally on trench JFET that we make gives you the lowest specific on resistance per unit area for really any class of voltage device. This impact is very pronounced at 650 volt, where the on resistance per unit area is down to 0.75 milliohm centimeter square. Normally on trench JFETs by themselves are useful for current limiting and current protection applications. But in order to use them for switching applications, they are turned into normally off devices at low voltages by forming cascodes with low voltage MOSFETs, and at higher voltages by forming a thing called a super cascode, where a series of them are connected to a low voltage MOSFET. Normally, off-trench JFET technology is not currently commercial. Uh, it is useful if you have extremely high temperature applications in mind. We also have silicon carbide planar MOSFET technology, which is useful especially at high voltages. It is in the future we will have trench technology at lower voltages. The specific resistance per unit area of our technology tends to be higher than what we can do with trench JFETs. Hence our focus on cascodes. To quickly understand what the differences are between cascodes and silicon carbide MOSFETs, it's the main thing to remember is the cascode from USCi is fully integrated. Uh, in a 3-pin device, it works exactly like any other MOSFET or IGBT with diode. The reason why the cascode makes a lot of sense is because you get the much lower RDSA of silicon carbide trench JFET technology, which leads to smaller chips with lower capacitances and also saves a lot of cost. You can see here a comparison of RDSA for 1200 volt silicon carbide JFETs compared to 1200 volt best in class MOSFETs. And because a silicon MOSFET is what controls the interface to the gate drive, you can use a wide range of gate drives, including the standard 0 to 12 volt that is common for MOSFET technology. But in contrast, most silicon carbide MOSFETs have to be driven with specialized drives from -5 to +15 or +20, and they're also low on the amount of overhead margin you have between the gate drive voltage and the peak voltages the device can sustain. Threshold voltages right off the bat are IGBT compatible with cascodes, generally lower for silicon carbide MOSFETs. The intrinsic diode performance of cascodes is excellent. It has low QRR, which doesn't change over temperature, and also a very low forward drop. More about this later in the presentation. In that sense, also, it's better than MOSFETs. Devices are avalanche capable, so are silicon carbide MOSFETs. But USCi cascodes are very strong in short circuit, and this is a rating that's provided on the datasheet. With MOSFETs, not so much. The ease of use factor for the cascodes comes from the fact that the silicon MOSFET allows you to drop this cascode device into a socket that is currently using a silicon superjunction MOSFET or a socket that's using an IGBT with an FRD or even any company's silicon carbide MOSFET. The gate voltage range of our latest devices is plus minus 25 volts, So it can be really drop-in replacing any of these types of switch technologies with minimal change to your existing circuitry. So this is how it works. The configuration calls for the gate of the JFET to be shorted to the source of the MOSFET, the drain of the MOSFET to be shorted to the source of the JFET. When you apply a positive voltage to the gate of the silicon MOSFET, this voltage becomes zero. Hence, the gate source voltage of the JFET is zero. It's on. The switch is on. When this gate voltage is dropped to zero, the drain voltage of the MOSFET rises to the level that reverse biases the JFET gate source, turning it off. The JFET turns off. So it essentially just follows the on-off signal of the MOSFET to turn the composite switch on and off. The device in the third quadrant works exactly like a MOSFET or an IGBT with an FRD. What actually happens in the cascode when the channel is off, the current flows through the body diode of the low voltage MOSFET. This ensures that you get a plus zero point 0.7 volt bias on the gate of the JFET, leaving the JFET on, so the current then simply flows through the channel. If you decide to turn the MOSFET gate on, you can avail yourselves of the benefits of synchronous conduction, because now the current simply flows through the channel of the MOSFET and through the channel of the JFET. So this is really how the quadrant 3 operation works. These MOSFETs are custom designed to have very low built-in charge, QRR, combined with the fact that the current flow in the JFET is simply through the channel, there is no stored charge. You get very good QRR characteristics for the composite cascode device. So this is a picture of what's in the cascode packages. They are co-packaged side by side. That's the silicon MOSFET sitting on an isolator. That's the silicon carbide JFET die. They are interconnected in the package. From the outside, you're looking at gate drain source like any other device. It is typically driven with a lower RG on and a higher RG off, which is a little different from most switches on the market, which usually prefer a smaller RG off because they're kind of slow, and a higher RG on. Uh, if you Sometimes in some circuits a ferrite bead can be useful, but is not necessary. Looking at the on-state characteristics, you will see from these on-state characteristics at room temperature and heart that the cascode is like any other normally off switch. It turns on beyond its threshold of 5 volts, and then the current increases as gate voltage increases. The RDS on increases with temperature, as you can see from the change in slope in this region. One thing to observe, though, is there is not a significant change, in fact, almost no change, in the saturation current once the gate voltage goes over 8 volts. And that is because the cascode is designed as two switches in series. We use the JFET to control the peak saturation current in the cascode. So as the gate voltage rises, you arrive at the point where the JFET takes over controlling the peak current, and then you see no further change in this current with gate voltage. The RDS on versus temperature characteristic look very similar to regular silicon MOSFETs. There is a 2x or higher temperature coefficient from room temperature to 150 C. This is current, and this is RDS on changing with temperature. So this makes it easy to parallel from a current conduction point of view. Device capacitances, when measured at the external three terminals, look like a regular MOSFET. Here's the CISS, the output capacitance COSS, and the CRSS. You will note that the COSS is quite low. This is a 1200 volt 60 milliohm max device, but the CRSS is almost zero. The Miller capacitance is very low, and this is a consequence of the cascode structure. The gate charge curve in the cascode comes from the low voltage MOSFET. The QGD in a cascode is usually not useful for predicting turn-off losses. That is actually controlled by JFET switching dynamics. However, the gate charge curve is useful for you to assess what level of gate drive power you need. This is a plot of the diode recovery behavior of the 1206K, which is a 1200 volt 60 milliohm max cascode taken at 800 volt and 30 amps. You can see that the QRR is extremely low, and this is really beneficial for all hard switch circuits. Looking at the inductive switching behavior of the cascode, this is the turn on and the turn off. Uh, Both turn on and turn off are extremely fast. Turn off is in fact extremely fast and has to we usually recommend using 20 to 40 ohms of gate resistance to slow down the turn off if you're in a TO to 47 package. Controlling cascodes has always been difficult. However, our design internally uses the gate resistances in the JFET and the MOSFET and the special characteristics of the custom designed MOSFET to allow a certain degree of DVDT and DIDT control. So what you see here is the eon loss plotted versus current for different values of RGon. And these charts show you, for those conditions, what range of DVDT and DIDT control you can bring to bear. And the same data is taken here for turn-off. Turn-off tends to be extremely fast. You will notice that turn-off losses are very, very low. The DVDTs can be very fast, but you can actually slow it down in this range using this range of gate resistances. Turn-off DIDTs can be as high as 8,000 amp per microsecond, but you can slow them down to about 3 kiloamp per microseconds. This is a chart that shows you the fact that the eon and EOF versus current is dependent on the kind of freewheeling diode you actually use. So in a chopper circuit, you would use a junction barrier Schottky diode. In a half bridge, you would use a cascode. So the blue curve is for the cascode. Due to its somewhat higher capacitance than a simple Schottky diode, it gives you a somewhat higher eon. This is what you would get in a chopper using a diode. Turn-off loss is about the same in both cases. The whole reason one makes these wide bandgap switches is because they allow you to have much faster switching, whether it's at room temperature or high temperature. So you can see here the cascode switching. This is EOF and EON data. It's not very temperature dependent. By comparison, here is data for an IGBT, which is significantly more temperature dependent. And you can clearly see that EOF for cascodes is much, much lower than IGBTs, as is EON. So you can use them at for higher frequency switching. You can actually use them drop-in replacement with just changes to the RG values to slow down the cascode and still avail yourselves of this efficiency benefit. Short circuit behavior of the cascode is very interesting. Uh, like we saw in the IDVD curves, once the gate voltage goes above a certain level, the saturation current is controlled by the JFET. So for that reason, the peak saturation current you see in short circuit stops changing. This is very beneficial because it means you can do your turn on loss optimization with gate voltage without worrying about the impact to the short circuit capability. The short circuit capability of 4 microseconds that we guarantee is guaranteed under all gate voltage drive conditions. Now, why does the cascode make so much sense? Not only is the JFET technology able to deliver a smaller chip size with its lower capacitances, the third quadrant behavior of the cascode is so good that there is no need whatsoever, either for forward drop or for reverse recovery, to use a Schottky diode. There is no degradation mechanisms uh, uh, from the crystal in the silicon carbide cascode that would force you to avoid body diode operation and use a Schottky in parallel. So here's a benchmark set of benchmark data that's been taken with a MOSFET plus Schottky uh, in a half bridge. MOSFET and Schottky high side, MOSFET and Schottky low side compared to a cascode high side, low side. You can see from the turn-on losses are lower because you don't have to recover the capacitance of these two devices. It's just the capacitance of this device. And cascodes, of course, are very fast for turn-off. And here we have inserted a larger resistance to slow it down to be at roughly the same levels of DVDT. So the bottom line is you can get equal or better losses while using almost 1/4 the total amount of silicon carbide. Delving further into the way the body diode works, so we did explain before that in quadrant 3, when the gate source is shorted, current flows through the body diode of the MOSFET through the channel of the JFET. In synchronous conduction, you can turn the MOSFET on, leading to even lower forward drop. So the cascode built-in diode has a much lower forward drop. If you combine a silicon carbide MOSFET with a Schottky, you can get into the same range of forward drop. However, a standalone MOSFET usually has much worse forward drop. So does the FRD in a silicon IGBT, especially if it's a fast recovery diode. In terms of QRR, there is no comparison. If you were to look at all the available alternatives, the Cascode gives you the best QRR performance. Looking at the IV curves of the body diode in the third quadrant, you can see the Cascode goes to a knee voltage of zero point 0.7. That comes from the junction diode in the silicon MOS. And then you see the series resistance of the JFET channel. That's it. And if you turn the gate on, you get the resistance of the Cascode in the third quadrant. This is synchronous conduction like with any other MOSFET. These, on the other hand, are the third quadrant curves of using a silicon carbide MOSFET. You can see that with VGS equal to 0 or negative gate bias, the forward drop tends to be much, much higher. And then looking at the actual QRR curves of the various devices, these have been taken at 150C. You can see that the Cascode offers the lowest QRR of all the different options, whether you use a silicon carbide MOSFET on its own or you try to combine it with a JBS diode. One thing though to watch out, uh, the Cascode is a very fast switching device. In a TO247 package, there is a considerable inductance. We find that if users do not use a minimal value of RG off, like 10 to 22 ohms, for example, if you try to use 0 ohm, internal oscillations can occur, which can lead to higher losses. So it is strongly recommended that even for the freewheeling diode, when you use a Cascode in a half bridge, even the diode operations require that RG off be in the 10 to 20 ohm range. So what is especially useful now with this ultra-low RDS-on JFET technology is what it can do for the 650 volt class of products. Traditionally something that silicon carbide has not done, but with the help of silicon carbide trench JFETs, you can make ultra-low RDSA switches, and when you put that together in a Cascode at 650 volt, you can get very good performance. So this is the datasheet for our USCi 6505K, which is a 45 milliohm max, 31 milliohm typical 650 volt class Cascode device. Why it makes sense is shown in this table. This RDSA of the silicon carbide JFET, which controls the entire cost structure of the Cascode device, is only 0.75 milliohm centimeter square. Compared to silicon carbide MOSFET technology or GaN-HEMT technology and silicon superjunction technology, this means the chips are much, much smaller. So even though silicon carbide is expensive, it's really not that much more expensive than silicon devices. So there is room now to start approaching cost parity using the die shrink that's possible with the trench JFET technology. You shrink the die, the other big benefit is the capacitances are lower. So this leads to a better EOSS behavior. Silicon carbide devices and our Cascodes are both avalanche and short circuit capable, and that's a key advantage they have over GaN devices currently in the market. One factor to think of is that as the chip size shrinks this much, you do need to pay attention to the thermal resistance uh, and factor that into your considerations during the design phase. And USCi is pioneering improved ways of manufacturing the Cascode to provide higher current density from these small chip areas. Here's a comparison of what the key benefits of the Cascode are. There's a comparison of chip sizes taken on actual devices. That's a 27 milliohm silicon carbide JFET combined inside the package to make the 31 milliohm typical resistance Cascode. So that's our specific on resistance. That's a silicon carbide MOSFET, a GaN HEMT, and a silicon superjunction device with much higher RDSAs. And the RDS EOSS product also, as you can see, is best for the Cascode. The threshold makes it easiest to use with standard gate drives, and these devices are avalanche capable. So the main areas where they bring a large benefit over superjunction devices is really not in direct switching. It's really in circuits where you need a soft, very low QRR body diode, such as a totem pole PFC. So this huge improvement in diode performance means that many more circuits are now possible with these devices. Uh, This example here is much simpler. It's just comparing a silicon superjunction MOSFET to the Cascode in a simple phase shift full bridge circuit, operating not at some crazy high frequency, but just at 75 kilohertz. So if you have existing designs that need improvement, this is a drop-in replacement part that can give you a quick bang for your buck without a whole system redesign. We have had a lot of success dropping in the 650 volt Cascode into LLC circuits. If you were to lose ZVS during LLC, because the body diode is so good, there is no danger of destruction of the device, and your baseline efficiencies are also uh, quite good because the RDS on capacitance characteristics are quite good. These are just examples taken, take examples from 3 different customers who have successfully used our devices in LLC sockets. So looking at these characteristics, it is fairly obvious what the key applications are going to be for these devices. This chart just summarizes the main areas where cascodes are applicable. And the 650 volt devices are especially well suited to serve the power supply market for servers and data centers. The 1200 volt devices are very popular now in battery charging applications, and we'll review some of these circuits in the next few slides. And of course, the traditional area where silicon carbide has already made significant inroads is renewable energy and storage. Here's our demo board test result from a phase shift full bridge using the 650 volt Cascode compared to a CFD part of similar RDS on from Infineon. You can just see from the waveforms, the sharp gate waveforms and the sharp drain source waveform, the capacitance benefit of the device and why the efficiency is higher. And since it can be a drop-in replacement, utilizing these in applications should be fairly easy. Totem pole PFC seems to be the new trend for in the near-term future to try and improve the efficiency of the PFC stage by eliminating the input bridge. And for this, what you require is devices that are capable of hard switching at high frequencies with low losses. And key to that is having excellent diode recovery. So this data is taken from a USCi demo board with our devices hitting over 98.5% efficiency at full load. Devices, you get a certain energy loss per cycle because of the internal physics. And this energy loss per cycle is actually lowest for our Cascode devices. This is extremely useful because now we could easily combine a Cascode, put a low voltage logic level MOSFET in here for low gate drive losses. Combined with these low intrinsic losses, Cascodes can be used to very high frequency. Paralleling. We get the question often about how to parallel Cascodes, whether they can be paralleled. So here's an example of paralleling of 8 devices, uh, high side and low side in parallel. Up here is switching curves taken for 4 high, 4 low paralleled, operating at 108 amps. You can see from the quality of the switching waveforms that with good board layout, paralleling is no problem. Uh, because we offer both 650 and 1200 volt devices, we have built TNPC demo boards to assess the operation of these devices in TNPC configuration. This is data taken at high current using four sub-blocks of TNPC operating in parallel. You can see that very fast switching is possible. All of these switching times are under 15 or 16 nanoseconds. So useful for implementing high frequency versions of these multi-level converters. So a key application for these devices, given their excellent switching characteristics, is battery chargers. And a key circuit we find prevalent in the market is the high voltage phase shift full bridge. Uh, the devices, especially the 1200 volt devices, are very well suited to this operation. And for lower output voltage battery chargers, as you might find in forklift chargers, for example, the same devices in phase shift full bridge are very useful. The because the cascodes can switch so well in hard switch circuits, uh, the 1206K, 1210K, and other Cascode devices we offer can be used in these configurations. And if multi-level topologies are implemented for higher bus voltages, the same devices have been shown to work very well. So these circuits can really simplify uh, customer applications where people are trying to use more complicated schemes like the Vienna rectifier with superjunction MOSFETs. The high voltage phase shift full bridge, there is a demo board from USCi to assist you with the design of our components. You can get extremely high efficiency even at 800 volt operation. The key devices we offer are the Cascodes, and where you need them, the Schottky diodes made out of silicon carbide. For solar inverters, like we showed earlier, the devices are perfectly useful for implementing the three-level NPC or the TNPC type inverter. The device types useful in this application are the 1200 volt cascodes if you're doing the TNPC along with the 650 volt cascode, or just 650 volt cascodes if you're implementing the three-level NPC, and we have all the necessary Schottky diodes to go along with them. So in summary, USCi offers the best-in-class silicon carbide diode technology. We have used our best-in-class silicon carbide JFET technology to build really these amazing silicon carbide cascode devices with lots of performance benefits, ease of use benefits, and they are applicable to a wide range of circuits as we have just discussed. They also have very few reliability concerns because they don't have the gate oxide issues that you get with silicon carbide MOSFETs or the body diode issues. Ease of use comes from the standard silicon interface. You can drop in, replace silicon MOSFETs, silicon IGBTs, or even other silicon carbide MOSFETs. The 5-volt threshold voltage is useful if you want to avoid a bipolar gate drive. From a cost point of view, especially at 650 volt, we showed that the ultra-low RDSA makes chip shrink possible to the point where silicon carbide cascodes from USCi can directly compete uh, in a reasonable way with silicon superjunction MOSFETs. Any other details you need as far as datasheets, app notes, SPICE models are concerned can be found on our website, and uh, contact information for our various departments is also available from our website. Thank you.